Section 5.3 is called the Fundamental Theorem of Calculus. So you know it must be a pretty big, important section called the Fundamental Theorem of Calculus. At this point in your mathematics career, you do know two fundamental theorems of mathematics. You know the fundamental theorem of arithmetic and the fundamental theorem of algebra. In short, the fundamental theorem of arithmetic it has another name. It's called unique prime factorization. And the fundamental theorem of algebra you would have seen in college algebra. So I'm just going to present to you now the fundamental theorem of calculus. If a function f is continuous on closed interval AB, and big F is any antiderivative of f on AB, then the definite integral, which we remember is the limit of a sum, the definite integral from a to b of f of x dx equals big F evaluated at b minus big F evaluated at a. This tells us exactly how to evaluate a definite integral. So here's some facts. If we can get an antiderivative for our integrand, little f, we now have a way to evaluate the definite integral. Second fact is a notation that everyone uses. So when doing the integral from a to b, f of x dx, you get your antiderivative, which is big F here. And so you write down the antiderivative, you make a vertical bar, and you put the lower limit of integration at the bottom of the vertical bar and the upper limit of integration at the top of the vertical bar, and then you evaluate. You do f of b minus f of a, big F of b minus big F of a. And notice there's no c here. There's no constant. You had to remember the constant when doing an indefinite integral. There's no constant here for several reasons. If you were to put a constant in there, when you do f of b minus f of a, the constant would cancel out. Second way to look at it is, it says, big F can be any antiderivative of little f. So you could pick the antiderivative that had a constant of 0. So probably the most important thing we can do right now is practice using the fundamental theorem of calculus. So I have a couple of examples here. Please write these down because you know the drill. I'm going to go to the board and I'm going to work through them. This is our work. First one's utilizing the fundamental theorem of calculus. And then I'm going to have a few that I'm going to want you to try. So write this down, get it in your notes, because I'm heading off to the chalkboard to work through it. All right, folks, now we know the fundamental theorem of calculus, so now we know how to efficiently evaluate a definite integral thanks to the fundamental theorem of calculus. So here, we're going to evaluate the definite integral 1 to 3 of x squared minus 2x plus 2 dx. So we get an antiderivative. So it's 1/3 x cubed minus x squared plus 2x, and then I make a vertical bar, put the lower limit of integration there, the upper limit of integration there. So the fundamental theorem of calculus says you evaluate the antiderivative at the upper limit, that's the f of b. So I put 3 in for the x's. So let's see, that's a 1/3 3 cubed minus a 3 squared plus a 2 times 3 minus, now I put the 1 in, and that's a 1/3 times a 1 cubed minus a 1 squared plus 2 times 1. So again, all of this here, that would be the capital F of 3. It's evaluating the antiderivative at the upper limit 3. And all of this here is f of 1. So now it's just a matter of doing it. So if I just kind of do all the arithmetic here, I should end up with 14/3. I'll leave the arithmetic to you. Part B. Evaluate the definite integral 0 to pi over 4 secant theta tangent theta. So we begin by getting an antiderivative. Well, the antiderivative of secant theta tangent theta is just secant theta. So we have the secant of pi over 4 minus the secant of 0. Now, off the top of my head, I might not know what the secant of pi over 4 is, but I do know the cosine of pi over 4. I know from the unit circle that's the square root 2 over 2. Well, that tells me the secant of pi over 4 is 2 over the square root 2. Likewise, I know cosine of 0 is 1, which tells me the secant of 0 is 1. So I now know what this is. Secant of pi over 4 is 2 over the square root 2. Secant of 0 is 1. And if for some unknown reason you don't like radicals in the denominator of a fraction, you could rationalize this. And that would rationalize down to square root 2 minus 1. Remember, you'd multiply by square root 2 over square root 2. All right, so you know I'm going to want you to practice some of these. Being able to evaluate a definite integral is dreadfully important. So in the section 5.3 exercises, I would like you to do numbers 30, 34, 44, and 56. So go to section 5.3 exercises, pause the video, do 30, 34, 44, and 56. Once you're done with them, I'll be here at the board working through them, and hopefully you'll have correct answers. All right, folks, in 30, you're asked to integrate from 0 to 2, 3x squared plus 2x dx. Get an antiderivative. Antiderivative is, well, just x cubed plus x squared. Evaluate that from 0 to 2, so 2 comes in for the x, and you get, well, 2 cubed plus 2 squared minus 0 cubed plus 0 squared, 12. Hopefully you got 12 for number 30. For number 34, you're integrating from 0 to pi over 4 to cosine x. So you get an antiderivative, which is 2 sine x. And let's see, that gives us 2 times the sine of pi over 4 minus 2 times the sine of 0. Sine of pi over 4 is square root 2 over 2. Sine of 0 is 0. Hopefully you got square root 2 for number 34. 44, integrating 0 to pi, 1 minus sine x dx. So you get an antiderivative, which is x plus cosine x. So you evaluate that from 0 to pi, so that gives you pi plus cosine pi minus 0 plus cosine of 0. So that's a pi, well, cosine of pi is -1, so plus a -1, so that's a -1. Minus, well, cosine of 0 is 1. Pi minus 2. So hopefully you got pi minus 2. And you had one more, number 56. So bear with me as I erase some stuff here so I can put number 56 up here on the board. And 56 was integrating from 1 to 2, x squared plus 6x plus 8 over x to the 4th plus 2x cubed dx. All right, I have to do a little bit of work here on the integrand. So when I look at the integrand, that numerator factors to x plus 2 times x plus 4. The denominator, well, there's a common factor of x cubed that I can factor out. That leaves me with an x plus 2. Oh, then a neat thing happens. I cancel out the x plus 2's. That's kind of cool. So I'm left with integrating from 1 to 2, x plus 4 over x cubed dx. And since the denominator is a single monomial, it's a single term, I could rewrite the integrand as x over x cubed plus 4 over x cubed. Well, x over x cubed, bases are the same, so I would subtract the exponents. So x over x cubed, that simplifies to x to the negative second. And 4 over x cubed, I'll write that as 4x to the negative third. So I get my antiderivative now. So let's see, I add 1 to the exponent. Out here I put the reciprocal of the new exponent, so that's just a negative 1. Here I add 1 to the exponent. The little multiplier that come out front would be a negative 1/2. So 4 times negative 1/2 is a negative 2. And now I need to evaluate this from 1 to 2. So I'm going to pull it up here, because to help me in the evaluation, I'm going to get rid of the negative exponents. So I'm going to write that as a negative 1 over x minus a 2 over x squared. All right, so here we go. Fundamental theorem of calculus. We get a negative 1/2 minus 2 over, okay, 2 squared is 4, so 2 over 4 is 1/2 minus a negative 1 minus, let's see, minus 2. Oh, that isn't too bad. So negative 1/2 minus 1/2 is negative 1. Negative 1 minus 2 is negative 3. So minus a negative 3 makes that plus 3. So for 56, the value of that definite integral is 2. All right, let's head back to the slides and see what's coming up. All right, so now that we're getting some practice evaluating definite integrals thanks to the fundamental theorem of calculus, let's check out this example. Consider the region that's bounded by the graphs of y equals 1 plus square root x equals 0, x equals 4, and y equals 0. The first thing we're going to do when we head off to the board is we're going to sketch the region that's described. Then we're going to write a definite integral to represent the area of the region. So a and b, nothing new there. Then in part C, we're going to use the fundamental theorem of calculus to evaluate the definite integral in part B, and as a result, that is going to give us the area of the shaded region. So let's head off to the chalkboard and let's work through this example. All right, folks, in this example, I asked you to consider the region bounded by the graphs of y equals 1 plus square root x equals 0, x equals 4, and y equals 0. Part A, sketch the region. Part B, write a definite integral to represent the area of the region. And then in part C, use the fundamental theorem of calculus to evaluate the definite integral that's in part B, which will find the area of the region. So, well, let me come over here for part A. The x-axis is y equals 0, the y-axis is x equals 0, so I already have 2 of the 4 things graphed. The graph of y equals 1 plus square root x, well, that's just square root x shifted up 1 unit. So it looks something like this. And then x equals 4, well, x equals 4 would be this vertical line. So we're talking about the region that is bounded by those 4 graphs. So it's bounded by the y-axis, the x-axis, x equals 4, and 1 plus square root x. We're talking about that region right there. Part B, write a definite integral that represents that area. Well, the definite integral that represents that area is the definite integral from 0 to 4. The integrand is 1 plus square root x dx. That's it. Part C, we use the fundamental theorem of calculus to evaluate that definite integral and find that actual area. So this is the part I'd like you to do. Pause the video, do part C, get yourself an antiderivative, use the fundamental theorem of calculus. So pause the video, do that, do part C, then restart the video. I'll be here at the board to make sure that you have it correct. Alright, here I go. I'm going to see if you have part C correct. So let me bring that definite integral over here. And I'm going to go ahead and rewrite square root x as x to the 1/2. Get an antiderivative. So that's x plus, let's see, the new exponent is 3/2. Add 1. Reciprocal of the new exponent goes in front. So now the fundamental theorem of calculus says we have a 4 plus 2/3 times 4 to the 3/2 minus 0 plus 2/3 times 0 to the 3/2. So I'm looking at this 4 to the 3/2. I think I can evaluate that without a calculator. 4 to the 3/2 power, that's the same thing as 4 to the 1/2 power quantity cubed. That's an old rule of exponents. An old rule of exponents that says when you have b to the n raised to the m power, you multiply the exponents. Well, 4 to the 1/2 is the same thing as the square root of 4. Square root of 4 is 2, and 2 cubed is 8. So we have a 4 plus 2/3 times 8, and all of that's 0, so minus 0. So that's a 4 plus, okay, 2/3 times 8, that's 16/3. 4 plus 16/3, get a common denominator, I get 28/3. So 28/3, that's the area of that region. So, hey, let's head back to the slides. All right, folks, this example, when you check it out, I'm saying let's let big F of x equal the integral from 0 to x of t squared plus 1 dt. And let's determine f prime of x. You know what? Write this down. We need to head off to the chalkboard and work through this. All right, this example, it may seem a little bit weird, but it's leading up to something. So let's kind of work through it. I'm saying this function, capital F of x, is equal to the definite integral from 0 to x of t squared plus 1 dt. Let's compute the derivative of that function of x. Well, once I know if I know what the function of x is, it's easy to get the derivative. We have rules of differentiation. So maybe I should begin by doing this. Doing the integral from 0 to x of t squared plus 1 dt. I mean, I can get an antiderivative here. It's 1/3 t cubed plus t. I can use the fundamental theorem of calculus to evaluate it. I get a 1/3 x cubed plus x minus, well, the zeros go in, so it'd be minus 0. Folks, this is it. This is that big F of x. That's the capital F of x. And now it's very easy for us to differentiate it. Differentiate it, we get x squared plus 1. So this example was very easy, and it's also foreshadowing something I'm going to call the second fundamental theorem of calculus. You'll hear me say this on the slides, but doesn't it look like f prime of x is nothing more than taking the integrand here and evaluating it at x? That's kind of what the second fundamental theorem of calculus says. So let's head back to the slides and look at this second fundamental theorem of calculus. All right, hey folks, our work at the board in doing this example, it seemed to indicate that the derivative of f of x was nothing more than the original integrand, t squared plus 1, with the variable change to x. And that's because this example illustrates what some people call the second fundamental theorem of calculus. Other people call it the little fundamental theorem of calculus. I'll call it the second fundamental theorem of calculus. If f is continuous on open interval I containing a, then for all x and I, when you differentiate with respect to x, the integral from a to x, f of t dt, you simply get f of x. So it doesn't matter what a is. This is x. When you differentiate with respect to x, the definite integral, it's just this integrand replaced with x. It's just f of x. I bet you'd like to see a lot of these on your next test. Let's look at an example. Let's evaluate the following. Oh boy, you got 4 of them here. So please write down all 4. You're going to see A and B are not too bad. C's going to bring us back to an old topic, kind of reminiscent of the chain rule, as is D. So let's head off to the chalkboard and let's work through this example. All right, this example is meant to practice the second fundamental theorem of calculus. So part A, you're asked to differentiate with respect to x the integral from 2 to x square root t squared plus t plus 2 dt. It doesn't matter what that number is. One step, we're done here. It's the square root of x squared plus x plus 2. One step, done. Bet you'd like to see a lot of these on your next test. Part B, differentiate with respect to x the integral from x to 0, 1 over p squared plus p squared plus 1 dp. The first thing I have to do is I have to say, hey, I have to flip those. I have to rewrite that as the integral of 0 to x. And when I do that, a negative sign goes out front. So a negative sign goes out front. And now we are almost done. The second fundamental theorem of calculus says that this is nothing more than 1 over x squared plus 1. So part B, we had just one extra step. Now there was a part C and a part D. Let me write that up here. So part C was the d dx, the integral from pi over 2 to x cubed cosine t dt. And then part D was d dx 10 to x squared of 1 over a z squared plus 1 dz. All right, so now there's something going on here in part C. Look at the upper limit of integration. It's an x cubed. So let me just kind of circle that and say, when I look at this, I'm going, there's something brewing here. I mean, if I let u equal x cubed, we know what the derivative is. We know du dx is 3x squared. And du dx I can think of as that I'm doing this. In other words, I can rewrite all of this as d duing the integral from pi over 2 to u, let u equal x cubed, cosine t dt, and then I can take this and multiply it by du dx. Kind of sounds like a chain rule, doesn't it? Because I know what this is. This right here, thanks to the second fundamental theorem of calculus, is cosine u, and then I have du dx. Boy, it's really looking like a chain rule now, isn't it? Cosine u, I said u is x cubed, times 3x squared. So, kind of like, I wanted you to see there was like a chain rule here, and there's kind of like a shortcut, if you will. To ddx this mess, yeah, it starts off the same. You put the x cubed in for the t, like the second fundamental theorem of calculus says. But then you have to remember to multiply it by the derivative of this x cubed, which is 3x squared. We didn't have to worry about this before when we just had an x up there, because the derivative of x would be 1, so we'd just be multiplying it by 1. So, part D is very similar to this. So here's what I'd like you to do. I'd like you to pause the video, and I'd like you to try part D and see if you could get part D. And then restart the video, and I'll be here at the board to make sure you're correct. All right, folks, so here on part D, I'm just going to kind of cut to the chase. I'm going to just kind of do it, with my shortcut idea, knowing the chain rules taking place. So the second fundamental theorem of calculus would give me a 1 over, I put x squared in for z, so x squared squared is x to the 4th. And then I have to remember I multiply that by, this is like the chain rule stuff, the derivative of x squared. Or if you wrote it like this, that would be fine. So that was the final topic here in section 5.3. The main thrust of section 5.3 is getting yourself very happy and familiar and proficient with using the fundamental theorem of calculus. We will see the importance of the second fundamental theorem of calculus at the beginning of our next chapter. So you're good to go. You can do all the exercises now. So go do the exercises in section 5.3, and thanks for watching.